All right, so today I actually want to talk about the two topics, and if we have more time, we can talk about other things. And if you have any question or comments, you can ask as well at the end of my discussion on the effects of mutation and the equilibrium and the varieties of stability. Um, so these are the topics that I believe Ricardo talked about in the previous week. So we can talk about them as well. So first and foremost, the one of the most interesting, one of the interesting questions in evolution is the effects of mutation. Now, what would be intuitively apparent is that mutations can have three different effects, right? So mutation, so let's look at the three types. So it can have a positive effect, they can have a negative effect, or they can have no effect, just a zero. So they can be neutral, meaning that they have zero effect. They can be positive or negative, assuming that there are no interactions between mutations. So mutations, uh, the way we are talking about right now, they really don't interact with each other as such. They just have an effect in isolation, and when you put them in an individual, an organism, the effect is going to be manifested in that organism, right? Now the question is, which is a difficult question, is how many mutations are positive on average, how many mutations are negative, and how many mutations are neutral. And that has different ramifications. So if most mutations are beneficial, then adaptation is much simpler to occur because there's a wealth of beneficial mutations. If mutations are mostly neutral, then evolution is purely just change in the frequencies of mutations that have no effect whatsoever. And if they're mostly negative, then selection would act accordingly as well. Now, what would be your intuition apropos the effects of mutations? So would you expect most mutations to be negative or positive or neutral? So you can feel free to so negative is the first answer. Anyone else? Negative. Sarah as well says negative. Okay. And Joseph also negative. Kawasi, hopefully, I do apologize beforehand if I mispronounce names. I'm not really a well, not a linguist, but I'm not a linguist, definitely. But I also I don't have a large number of people with different friends with different names. So just generally every name is new to me. So as one of you pointed out, is that the case that the neutral ones are the second most common? So what I'm going to show you is this plot on the y-axis when it says f is the frequency. On the x-axis is just plus and minus, and actually there should be a zero in the middle as well. So that will be the mutational effect. So mutations are, so if you are on the right side at the very edge of this plot on the x-axis, you are extremely positive. If you are at the leftmost side of this plot, you are extremely negative, and you can be somewhere in between. So the way usually these mutation studies are done, and there are two types of them. There are mutation accumulation ones. Mutation accumulation studies, which I think Ricardo hasn't talked about yet, but those are one types of simple ones that you can use, which I think we come across later. The second one are the directed mutations. So directed mutation and studies are studies where you just simply insert point mutations into a structure to see into a genome to see if the effects are negative or positive. So, for example, oh no, I don't want that circle. Delete that. So let's say we have a genome. So I'm going to use a rectangle to show a circle as a genome. So this is a genome of an organism. Let's say E. coli. E. coli. Right. So the idea for a direct study of mutational effects would be to simply create organisms where they have different mutations. So, for example, the first one has a mutation here. So it's the first mutation. Someone else has a second mutation. Someone else has the third mutation, etc., etc., until you cover the entire genome. And the idea being that you can get all these different mutations in an organism and then measure the effects, which in this case would simply be fitness, right? So it should be, so it is just the fitness of each organism. So that would be, if I write fitness as W, so it would be the fitness of the first one. So that would be the fitness of the organism carrying the first mutation, the fitness of the organism carrying the second one, the third one, etc., until the last one, the nth mutation, right? So then you end up with a library of organisms, each carrying a different mutation, and each mutation has effects. So it has this fitness effect. And since no two organisms are carrying two of the mutations, we are measuring the mutational effects in absolute terms. So we are not looking at the interactions, but we are looking at the simple effect of each mutation in isolation. So in one study, so in your textbook, they talk about a study using phage, so using the approach I just described, but applying it to a phage instead of a bacterium. And you know why, right? So why did they choose a phage over a more advanced prokaryote or a eukaryote even? Why not E. coli? Why a phage, which is a virus? It's a smaller genome, so I think a few of you are typing those. So simply, so you have smaller genome, so is the correct answer. Because in a lot of ways, it becomes a matter of technical limitations when you're trying to introduce all the possible mutations, and they didn't really introduce all the possible ones. But if you want to introduce a large number of mutations and create these libraries, it would be easier to deal with a smaller genome than a large one. So what they observed was that mutations are deleterious, and there are a bunch of neutral ones, and then there are a bunch of positive ones, but then the extremely positive mutations are not the most common mutations. Neutral mutations are the second most, at least in that study. So there are different studies, but in that study, as far as we are concerned, the second most common type of mutations was neutral ones, and then mutations are mostly deleterious. The idea that the mutations are mostly deleterious is actually simple and is quite intuitive, because in any complicated system, let's say we have a computer, right? And in the case of computer, what is the likelihood of you opening your laptop and bashing on the motherboard? What's the likelihood of that process making the laptop run better? Or what's the likelihood of you again opening your laptop and just removing uh, uh, units from the motherboard, or removing and replacing, or throwing away RAM, or creating new bridges between different parts of the board that were not previously connected to each other, and disrupting connections that already exist? What is the likelihood of that uh, experiment to result in anything but the total uh, destruction of the motherboard? Uh, it's very unlikely, right? So in any complex system, whenever you introduce a change, it's more likely to be negative than positive. So in that respect, the observation that if you introduce mutations, the bulk of those mutations are going to be negative is quite intuitive and reasonable. What is important to understand is that, as you know from the definition of selection, selection is working on these beneficial mutations, right? Uh, that's the selection. It's really not easy to write with the mouse, but there we go. So selection is acting on these mutations. So mutations that are slightly uh, um, beneficial to up to mutations that are extremely beneficial, and selection is going to act accordingly according to the effects of these mutations, right? So despite the fact that the bulk of mutations are deleterious, you still end up with adaptations because selection is selecting for beneficial ones as well. And it's more complicated than that. We're going to get to the nitty gritty of the process by which the mutational effect affects the selection process later after the Hardy-Weinberg stuff next week. So that would be the relationship between selection and effects. But so far, simply know that the mutation effects are deleterious at most. Now, before we move on to the equilibrium and the varieties of stability, any one of you has any question? Feel free to ask. Okay, so I'm assuming that no questions. So let's go to a topic that is more, slightly more complicated. That is the topic of equilibrium. Okay, so in order for us to say equilibrium, just I write EQ as just to denote equilibrium because it's pretty long word, relatively long. The idea of equilibrium is interesting. It's very common. It's not limited to biology. It actually comes from physics, statistical physics to be more precise. And the idea is in as far as the definition is concerned, it's pretty simple. So let's say that you have a system, any system. Let's say the system is a system of reactions, right? So you have a system where, believe me, if you understood the basics of equilibrium, it would help you quite a lot. It might seem a little bit abstract, but it's actually very helpful. So a reaction. So you have a system of two reactions. So there's A plus B becomes C, and there's C can also get destroyed, right? And on the y-axis, I'm just going to have the number of A, B, and C with different colors. So what I'm going to do is, okay, A going to be red, B going to be green, and C is going to be black, stay black, right? So when you start the experiment, so let's say, so you have these reactants A and B, and so the y-axis is concentration. Actually, I shouldn't use C for that, it's a bit confusing. So just remember that the y-axis is concentration. Now, when you start the system, in this case is a chemical reaction, right? You have two reactants, A and B, and you know that if you add them together with a given probability, they're going to combine and create C, but C itself can just get destroyed for some reason. And what happens is that when you start the experiment, you only have A and B, right? So you have half of the system is A, the other half is B. There's no C in the system. So the the x-axis is just time. So time. Right. So at the beginning, they're just A and B, and that's fine. They start reacting with each other, so they create C. So at some point, C appears in the system. Actually, C appears from the very low. So C should be here. And then over time, C slightly goes up. And B and C should also go down because they're being used. Okay, right? So that's how the system is behaving. And eventually, you run out of A and B if there's just a fixed number. And so A and B would become 0, and there's a C, and the C is slowly going to deplete. Actually, so let's get to the second reaction so we don't get rid of C. So eventually what happens is that you get, so if we have only one reaction, C would reach to 1, and A and B would reach to 0, right? So what's happening here? What is the situation? So we started with a system from this point on the at time 0 with 2 reactants. At the end, we got 1 reactant. This is at the end when you look at the system really doesn't appear to change at all. So you have a steady state, as they call it. So steady. So that's usually not interesting at all, because even though it's at the macro level, so at the when you just look at the test tube in which you put A and B, and at the end there are only C's in them, you don't see any reaction, but by the end of this by the end of the this reaction series of reactions where A and B are depleted, and there's only C in the tube. So when you look at the tube, there's only C, but at the molecular level as well, there's only C. Like there are no reactions happening. So the system is in uh, is in a steady state. It doesn't really change at all. So these are the types that are not really interesting. But what is interesting is a type of these behaviors, which is similar to steady state, where oops, what happened? So a type of these reaction systems where you have time. So again, so let's say it's similar, but the way A and B interact are different. And again, Y is concentration. So let's say you start from C starts from 0, but stays at some concentration, and B and C as well, they stay at a non-zero concentration, right? So at this point, you have, let's say, 80% C, and the other 20% are 0.1 A and 0.1 B, right? So in this case, when you look at the system at the test tube level, you see no reaction really, because you only see the fixed concentrations of A, B, and C. But at the molecular level, they are interacting because as opposed to the first example where we had the steady state, in this case, there are reactions happening at the molecular level, which keeps the concentration of C at 80%, doesn't allow it to go to 100%, and keeps A and B in the system as well. So that is an equilibrium. As a state where you have changes happening at the low level, but at the high level, you really don't see these changes, equilibrium. So that is a whole area of study in statistical physics, which we are not going to cover at all for better, I think. It's very complicated. But why does it have to do any, why is it relevant to what we understand? So usually when you look at, you try to understand how populations change, which is the whole point of evolution. You're dealing with alleles, right? So you have, let's say, an allele called A, and another allele. So that's actually A1, and another allele called A2. So these are alleles for the same, at the same locus, right? And if it's a diploid system, so these are the alleles, so you have a bunch of genotypes, right? So you have A1, A1, you have A1, A2, you have A2H. And in this case, when we have only two alleles, there are frequencies associated with the genotypes. Actually, so I have frequency associated with alleles. That would be easier. So we have the frequency of A1, so it's the F of A1. We're going to just call, we're just going to call that P. This, for simplicity, like doesn't mean anything. It's called P, and for F of A2, it's called Q. Right. So we have, so in this system, we have only two alleles, at the same locus, we have, because it's again for the sake of simplicity, we assume that the organisms we are studying are diploids, meaning that they have two sets of genomes. So each individual is carrying one allele, sorry, two alleles at any given locus. So we end up with three types of genotypes, which is A1, 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 A2, A2, A2. But then we have the frequency of alleles, the frequency of A1, P, frequency of A2, Q. Now, since since P and Q are frequencies and there are no other alleles in the system, mathematically it's obvious that P plus Q should be 1. Right. And whenever you have the genotype frequencies, you can simply understand that all the, so if you have the frequency of these three genotypes, you know that, so in the case of P, A1, they all have these alleles, so that frequency would directly feed into the frequency of P1. Half of the A1, A2 also carry A1. So half of them. So if you had the frequency of A1, A1 and A1, A2, you can just divide A1, A2 by half, add it to the frequency of A1, A1, and you get the frequency for P allele. And then since P plus Q equals 1, P minus 1, so 1 minus P would be Q as well. So these are just simple notations, not really the point of what we're doing, but they're important to understand what's happening. Now, I talked about the chemical reaction, and when I was describing stability. So in the case of population genetics, with this notation we just learned, we can create a similar plot to the one I had created for. So it's time and frequency on the y-axis. So in the previous one it was time and concentration, but of course concentration would be the same as frequency. So if we are looking at the frequency of P1, let's frequency of P, we can envisage a situation where P starts at very low frequency and reaches at some frequency in a resistor, right? So that point is just the equilibrium for P, right? So it's a point. So you start from a initial frequency, and it just reaches to some point. Well, how can you establish that this is actually the equilibrium? How can we be sure that this is equilibrium? That this is just not so how can we establish that if you started from another initial frequency of P, you wouldn't end up in some other place? How can we do that? Does anyone have any suggestion? How can we establish this is actually an equilibrium for P? Hardy-Weinberg? Hardy-Weinberg is not an equilibrium. Hardy-Weinberg is just results in equilibrium. So P plus Q equals 1. That's just that is true, of course, but that doesn't help us to find the equilibrium. So the answer is actually quite simple once you know it, which is an equilibrium is defined as a point where, regardless of the initial condition, you would get to that point, right? So if we started from a frequency of p equals 1, so that is 1, so, oh, right. So equilibrium, so a point can, so what we pointed out that its square frequency stops changing, but even if during so in this case, during evolution, as time goes by, if the frequency starts reaches some place, you still can't be sure that that's equilibrium. So in order to be certain that this is an equilibrium, equilibrium should be insensitive to initial condition. So it should be in initial independent. So it should be independent of initial conditions, right? So it shouldn't matter. So if it's really equilibrium, you should be able to just start from a different initial condition and reach to that point, and another initial condition and reach to that point. So all these evolutionary trajectories should converge to the same point. So in that case, that is an equilibrium, right? So that is simply to distinguish between any stability and or any fixed point versus an equilibrium. So if you reach a point and you don't change, that's just a fixed point. But in the case of an equilibrium, doesn't matter where you start, you just end up around that fixed point. So in that case, that fixed point becomes an equilibrium, right? So that's just simply the definition of equilibrium. Now we have we can define equilibria as having different stabilities, right? So let's. So what's the matter with stability? Stability of equilibrium. So stability is interesting. So stability is usually easy to imagine using simple metaphors, such as a kind of sort of a bump or a peak, a valley, and a flat land or flat space. So the idea is that in a stability, so if you reach a stable point, or sorry, when you reach an equilibrium, if we any small perturbation, if that results in you moving away, so this circle is on top of this peak, and so any slight movement of this, let's assume it's a ball on top of this, not a circle. So this black ball on top of this peak. So any slight movement of this ball would result in it just descending and hurling down the peak. So as long as it's exactly positioned on top of this peak, it's fine. But any slight movement, any small breeze would result in it just going downhill. What does it mean in the case of allele frequency over time? So let's say, so that's the frequency of P. So again, P is the frequency of allele A1 in this diploid system that we imagined. So let's say we start from this point. We reach the supposed equilibrium here. Now, what I can do to test if this equilibrium is stable is to change the frequency of P in one direction. So it's either reduce it suddenly or increase it. So what it means is I just playing God, as it were. I just take the allele out of the population so that the frequency of P would decrease or increase. So if I just take the individuals carrying A1 out of the population, the frequency is going to decrease. And if it's an unstable equilibrium, it's just going to go down, right? So it was so we knew that there's an equilibrium here, right? So at the point of equilibrium, I just perturbed the system a little bit, and after the perturbation, the system just kept going down, going away from the equilibrium. So if you don't perturb the system, so regardless of the initial condition, they're going to converge to the equilibrium, right? So it is a still equilibrium. So still, regardless of your initial condition, you're going to get to that point. But any minor perturbation, so perturbation simply means changing the amount of this the parameter of your interest. In this case, it's the frequency of p. So we perturb it. In this case, I took individuals carrying this allele out of the population, so the frequency went down. But because it was an unstable equilibrium, it just went down from there, right? So clear so far? It is an equilibrium, but when you change the frequencies slightly at equilibrium, it's going to move away from the equilibrium. So that's a simple case of a unstable equilibrium. So in the case of a stable is usually, you can imagine it as a valley. And so the same black ball, if we position it down this valley, sorry, the circle looks kind of weird, but so if we position it down the valley, any movement, so if we try to roll it up on either side, it's just going to come back down, right? So there's no way for us to change it in a way that would make it be at any point other than the equilibrium. So what it means in the case of, again, the frequency of the allele p over time is that, so again, we have already established that equilibrium is here. In this time, so again, in order to establish the equilibrium point, or equilibria if there are multiple ones, you have to start from different initial conditions, and all of them should converge to the same point. In that case, that's an equilibrium. So in this case, I started from some frequency, p is here, and now I do the perturbation. So in this time, I'm going to increase the frequency of p in the population. So I put the frequency here, and it's going to start going back down. If you repeat this experiment and this time perturb it down, it's going to go back up as well. So since it's stable, it's always going to converge back to the point of equilibrium, and that's the whole point of stability. Okay, so far two types of equilibria: stable or unstable. So in the case of unstable, any form of perturbation is going to result in you moving away from the equilibrium. In the case of a stable, if you, regardless of the amount of and the direction of perturbation, you're going to the system is going to return, converge to the equilibrium. So, any questions so far? So one of you asked, both unstable and stable come back to equilibrium eventually. No, so in the case of unstable, they don't come back. So in the case of unstable equilibrium, like the metaphor of a ball on top of a peak, when you move it away, it just moves away. It doesn't come back. It's just not possible, right? So if you imagine that the same way that the gravity is going to pull down the ball after it's moved away from the peak, a system that has moved away and from an unstable equilibrium is just going to move further and further away from it. And it's not going to have any pattern, right? So because it's not moving towards another equilibrium, if there's only one equilibrium in the system, it's just going to move away or in any direction. So that's a stable, unstable. One interesting is kind of interesting. Actually, I don't know if it's uh, more interesting than stable or unstable, but there's the idea of neutral. If I could, okay, so neutral. So neutral. So neutral equilibrium is where any movement. So if you move the, so in this case, it's a ball on a 2D plane. Also, so some of you, one of you asked, so for a some population will reach equilibrium under one. No, for unstables, they're just, no, so for unstable equilibrium, all the populations would, regardless of the initial condition, would reach to equilibrium, right? But once at equilibrium, if you perturb them, they're going to move away from it. So all of because it's an equilibrium still, regardless of the initial condition, you're going to get to that point. But when you are at that point, any perturbation results in you moving away from the point in question, right? Hopefully that answered your question. So in the case of neutral, so it's a 2D plane. So you have a rolling ball on a 2D plane, and if you nudge it on any direction, in any direction, it's just going to move in that direction, right? It's not going to come back. It's not going to move away. It's just going to move according to the amount of force you put into it. What it means is that in reality, when you look at the frequency, so again, we're looking at the frequency of P1, which is sorry, frequency of P, which is the frequency of allele, one allele in a diploid system. So this is the equilibrium again. We have started from this initial conditions. We just go down. At equilibrium, I perturb, and it stays there. From another initial condition, I go up, I reach equilibrium, I perturb down this time. It's going to establish a new equilibrium and stay there. So that's a neutral one. So in the case of neutral ones, you simply, every point is an equilibrium after perturbation. So you have an original equilibrium, which is where all the populations are going to converge to, all the frequencies are going to converge to it, regardless of the initial condition. But once at equilibrium, if you perturb it, it's just going to establish a new equilibrium according to the perturbation, according to the direction and the magnitude of the perturbation in question. And so these are the different types of equilibrium, different classes: stable, unstable, and neutral. And after, so there are examples of each in population genetics. For deleterious, beneficial, or codominant alleles that we're going to cover later, I think next week after Ricardo has covered the topics on population genetics. So any question? Any questions, comments before we wrap up this presentation? So any questions so far related to these topics, or anything prior to the population genetics stuff? So if you have any question, just write it down in the chat session, and I'll answer it happily in the last 10 minutes of our station. Again, you can type your question, or you can use your microphone. In order for you to use the microphone, you have to, I think, press the raise your hand button on top left of your monitor, and then I think I can just allow you to drop. Christine asked, could you explain the difference in the stability between stable and neutral equilibrium again? Absolutely. So in the case of a stable, so in the middle one, we have, and so in this case, there's only one equilibrium. The red line in the time series plot. So we start from a different, from an initial condition. We converge to that point. When I perturb, the frequency over time is going to return to the equilibrium, right? So in the example drawn here, I perturb it twice. So perturb two different trajectories. Once increase the frequency of P, in the other one decrease the frequency of P. In both cases, the frequency of P just bounced back to the equilibrium, right? So no matter what I did, it just went back to the original point. In the case of neutral one, which is the left one, in this case, so in the first, so in the upper one, when I started from the high initial condition, after it reached the equilibrium, I just perturbed it up, so increased the frequency, and after the increment, it just stayed there, so established a new equilibrium, which was simply the frequency prior to me adding more P in the population, and that new point became the new equilibrium. And the second trajectory, when I started from a low frequency of P and it reached equilibrium again, this time I decreased it so that I perturbed it by taking out the allele from the population, and it established a new equilibrium which is lower than the original one. So no matter what I do, so we can actually start from a different initial condition, right? Like here, reach equilibrium, perturb is going to establish a new equilibrium. So as you can see, every time I change it, it just creates a new equilibrium. It doesn't, so as opposed to unstable, it doesn't just simply move away from the equilibrium. It just assumes that the new point is an equilibrium. The idea being that since in this system, all points are stable, no matter what, when you move it to a new point, it's just going to stay there in the new point. So it's the same, the metaphor of a rolling ball on a 2D plane is quite apt because it captures the lack of preference for any point in the system. Hopefully that was clear. A clear explanation of what's the difference between stable and neutral. And by the way, just to remind you, as usual, all the recitations are going to be online. The previous two are already on. YouTube. So if you wanted to rewatch them, you can. And I usually edit them before uploading, so you're not going to just witness the riveting clip of me just drinking iced coffee while waiting for you to ask a question. So that is going to be cut out. Mhm. Again, any question, just write it down, type it, or you can even talk if you want to. I'll be more than happy to answer. All right, so if there is no question, we can conclude this session. As usual, during the week, we're going to have the normal recitations. The early one in the week, more of a review, and the second one covering the topics already, topics that will have been covered by then by Ricardo. The fascinating subject of population genetics, which is a slightly more complicated, but we are going to uh, soldier on and cover everything. So, if no question, have a great Sunday and see you next week then. All right.